Today we are talking about using regression to model data. In particular, we're going to be using our calculator and the regression function on it to model a set of data. So when we are given a set of data in a table form or just written out, whatever, it is very useful to find an equation, a function that best describes that data. Engineers and scientists have to do that all the time. Okay, usually they use software for that purpose, but we're going to see, the math behind it. Okay, on this first sheet of your notes, this is good stuff, but this was as if I wasn't in front of you teaching it. So I'm going to skip this first page, even though this is a good series of steps to return to if anything that I talk about is confusing to you. This is all written out on this page. One thing that we will want to do is grab your TI-84, or if you have a different calculator, you're going to need to figure out how to do this. Lots of YouTube videos for all the different types of calculators. So you go and figure out on your calculator how it works. But for the TI-84, we need to go to Mode and go to Stat Diagnostics and turn it on. Okay, so I'm going to do that. I'm going to make sure that my TI-84 that's turned on. So down here where it says Stat Diagnostics, mine is already on. If it's not, go highlight that and press Enter. Okay? Alright, that will allow us to see the R-squared value. And I will warn you that when you reset your if you reset your calculator for some reason, sometimes I found even when my battery goes dead or I need to charge it or whatever, it's going to default back to off. So when you're working, if you don't see an R-squared value when you're doing the statistics that we're doing, just go back to Mode, turn back on your Stat Diagnostics. Okay? Alrighty. That is going to allow us to, it's going to assist in telling us how good our set of data is. Alright? So, this series of steps are going to work for all of the different regression models that we're going to use. Okay. So, up here I have a brief recap of stats on the TI-84. So you want to go to Stat, Edit, get back my calculator up here, I'm going to quit. Okay, go to Stat and then Edit. There's the Stat key, so I'm going to push Stat, and then Edit is already highlighted, so I'm just going to hit Enter. And if you have not ever used this, then your screen should look like that. If you have used it, you might have a bunch of data in here, whatever. Okay? So if you do have data in there, there are two things that you can do. You can either push Delete and hold it down, and it'll scroll all of those and delete all of those. Or sometimes you have gone in, and we will do this, sometimes you've gone in here and hit some kind of equation for L1. If so, you're going to need to clear that out. If you push Delete up here, it's going to delete that entire list where you won't even see that column anymore. And you don't necessarily want to do that. So to keep the column but just clear out the function, you just go over here and hit Clear, and it'll clear L1. All right? Okay. So let's take a look at number 1 here. All right? We have the age and weight of 5 randomly selected babies from a particular pediatrician's office, and the age and weight are listed in this table. It says a linear regression is used. So we're going to perform a linear regression. Is used to construct a linear model for L. Okay? Alright, so we're going to go to L1 and L2. In L1, I'm going to put the age in weeks. So whoops, goodness. Go back there. I don't know what I did. 4, 5, 6, 8, and 12. Okay. And then over here in L2, I'm going to put the weight in kilograms. Okay, a word of warning. Lots of times when you get to this very last one and you have typed it in, you've typed in 5.7, it will not add it to your list until you press enter. Once you press enter, it'll be there. So don't forget that final enter, okay? It's a common mistake I see kids make. So at the end, just always push enter, okay? All right. Now, let's just get a feel for this. I'm going to just plot this data. So I'm going to go to up here where it's above the y equals in blue where it says stat plot. I'm going to do second y equals to get to stat plot. Right now, all of my plots are turned off. I'm going to press enter. I'm going to press enter on the on feature. This first one here is going to produce what is called a scatter plot. Just a plot of these ordered pairs. That's all it's going to do. Okay, so I'm going to leave that on. My X I want to be L1. My Y I want to be L2. And I'm just going to keep it with this one. If you would prefer to see a plus for each ordered pair, you can, or a dot for the point, that's fine. I like just this one, so that's going to work for me. And on my calculator, it lets me adjust what color I want to see those in. I'm just going to keep it at blue. Okay, now, this has a really nice way to graph a nice window for what we have in our ordered pairs. If you go to zoom, see down here on number 9, stat, if you hit number 9, it does the perfect window for that set of data. Okay? Now, here's the graph of these ordered pairs. Do you see why a linear regression is being used for this set of data? Do you see that a line could describe fairly effectively this set of data? Okay, that's what we're doing here. We are describing sets of data with different equations, different functions. And you will be told what type of function to use usually. Okay? Sometimes you're going to need to figure out what is the best type of data, given the situation, given the set of data. All right, so to find this linear regression model, this line of best fit, go back to stat, and then we're going to go over here to calc. Whoops, what did I do? Stat, I think I hit enter. Okay, go over here to calc, and here are starting on number 4, here are all of your regressions. Here's a linear regression in the form ax plus b. Here's a quadratic regression. That'll be for a parabola. Here's a cubic regression for a cubic polynomial. A quartic for a 4th degree polynomial. Here's another linear regression. I don't know why they didn't put these back to back, but they didn't. One is in ax plus b form, one is in a plus bx form. These two produce the exact same equation. Well, the exact same line. It's just one gives you the a with the x and one gives you the b with the x. It doesn't matter, right? ln regression, that's our natural log regression. That is our only log regression on here. There's no just log base whatever. That's the only logarithmic regression that this calculator has. Exponential regression, power regression. Okay, logistic regression. We're going to see what that is. Sinusoidal regression. It gives you a sine curve. And I've not played around with the manual fit. So these from 4 to, what did I end with? The C? From 4 to C, those are the regressions. So in this one, we're going to do a linear regression. It does not matter if you do the 4 or the 8. It doesn't matter. I'm just going to do the 4. Okay. The X list is going to be our Y1. The last time I used this, clearly I used L3. So I'm going to use L3 for, I want L2 to be my Y list. To get to those L's, look above the 1, 2, and 3 in blue. Look above these numbers. That's the quickest way to get to your L's, your lists. So I want L2, so I'm going to do second 2, and it changes it to L2. The frequency list. I really don't know what that means. I always leave it blank. So maybe when you get to stats, if you do take a stats course, you'll find out what that is. But I don't need that, so I'm not going to do it. I'm going to store my regression equation in for Y1. Okay, so I want to have Y1 there. The quickest way to get to Y1 is up here in F4. So that's in green, so I'm going to do alpha trace to get to all of my Y1, Y2, Y3, all of those. So I'm just going to hit enter on Y1, and now hit enter again. And the next time I hit enter, it will calculate the regression, the linear regression equation, and it will automatically store that linear regression equation in for Y1. So here is the equation. The form is y equals ax plus b, where a is 0.185 and b is 3.545. Okay. Look at r and r squared. The closer r squared is to 1, the better the fit is. All right? So this tells me that it's a fairly good fit. Not perfect, though. If it was perfect, this would be exactly equal to 1. Okay. So I'm going to hit y equals now, and there is my equation. It automatically stored it in. Now I'm going to hit graph, and we're going to see what is graphed here in Y1. There's the line. Okay. Some of the data are a little below the line. Some of the data are a little above the line. Okay. Alrighty, let's answer these questions now. Use L of t, that's the linear regression, to predict the weight of the baby that is 10 weeks old. There's a couple of different ways to do this. We can either go to our home screen by doing second quit and hit Y1 at 10. That gives us Y1 at 10 weeks. So I would expect at 10 weeks for the baby to weigh 5.395 kilograms using that linear regression model. So I would say 5.395 kilograms. Okay? The other way that we could have done that, and we were already on the, I hit graph again, we were already here. The other way to do that is to do calc. So second trace to get to calc and just get a value. I want x to be 10, so I'm going to hit 10 in for x, hit enter, and it goes right to where x is 10. And there's that 5.395. Okay? Take a look at part B. The weight of a sixth baby is 5.3 kilograms. Using the model for L of t, how old is that baby? Okay, I want for the weight to be 6.3. So to find that out, I'm going to go to my y equals, go into another y2, and type in 5.3. So it's going to graph y is equal to 5.3. There's y equals 5.3. All I need to do now is to find out where those intersect. So second calc 5 for intersect. Enter on the first, if I hit enter now, it'll make it the L of t regression model. If I hit enter now, it'll use y sub 2, that 5.3, and now it's asking me for a guess, and I'm just going to hit enter again because there's only one intersection here. There's the weeks, there's the weight. So at t is equal to 9.4864. Remember that you need to give at least 3 values after the decimal point. At least 3 values after the decimal point. Every time, unless you are specifically told to round it somehow in the problem. Okay? Okay? Alright, let's try another one. This table shows the population of a city every 10 years since 1970. This time we're going to use a quadratic regression to model the data. Okay, so let's go in, Stat, Edit. I did not change the function for L2, so I'm just going to delete. Just quicker for me to do that. Delete that list, delete this list, and I'm going to input my data. Remember, hit enter after that last one. Alright? I always encourage you to take a look after you enter it. Take another look and make sure that you entered it correctly. It's very easy to enter the wrong numbers. Okay, I always go back and check and make sure I entered the correct numbers. Okay, they're all in there, everything's good. I can go to, I don't have to go back to stat plot because it's still on, but I am going to go to y equals and clear out these regressions, okay? Let's find out what these look like. I'm going to do zoom 9 again so that it shows me all 5 of those points. Okay? So this point here, in fact I'll trace. That's the point 0, 489. 0, 489. If I go over, that's the point 10, 601, and so forth. Okay, you can always trace those. Okay? Alright. They're telling me to use a quadratic regression on this. Do you think that that's a good one to use for this data? Do you think that they should have told me to use a linear regression? It looks fairly linear. Well, I'm not going to override what they told me to do, even though this does look fairly linear. I'm not going to override it. I'm going to use what they told me to use, and I'm going to use a quadratic regression. So I'm going to go to Stat, Calc, Quadratic, number 5. I don't scroll down, I hit the number 5. L1 and L2 are still stored in for X list and Y list. I'm still going to leave the frequency list blank, and I'm going to store this list in for Y1 again, enter, and then enter again. Okay. This doesn't look that terrible, does it? So there's the equation where A is this decimal, B is this decimal, and C is that larger value there. Okay? So that's A, B, and C. So since A is positive, this parabola will be pointing up. Okay? So let's see what this looks like. If I go to y equal, remember, it automatically stored all of that in for y1 so that I don't have to retype it in there. That would be a pain. So I'm just going to hit graph to see this curve. Oh, that was better than I thought it might be. It appears that three of these values are super duper close, and two of them they don't look far off, right? So not a terrible model, apparently. Okay, so let's answer the questions. Using P of t, determine the projected population in 2030. Okay. Notice here, this was years since 1970. So when time is 0, when t is 0, that's 1970. This was 1980, 1990, the year 2000, the year 2010. What would t be at 2030? Well, at 2030, we're going to need 60 years after 1970, correct? So t will be 60 there. So I'm going to go to my home screen. I like doing that. So y1 at 60, at t equals 60. So this tells me that the population will be this many thousand. That many thousand. So if I wanted to write it just as a single number, that would be probably the multiple choice answer. I would multiply this by 1,000, and it would be that. Okay? Alrighty. So that would be the population in the year 2030. Using P of t, during what year will the population be 2 million? So this was 2,051,600. When will it be 2,500,000? So that is when P is equal to 2500, right? Because it's in thousands. So I'm going to go to my y equals, and then these are all the p's, right? So I want P to be 2500. Are we off the screen a little bit? Is 2500 off the screen? Maybe. Let's trace. Let's go up. Oh, it must be higher than our screen currently is. This happens a lot. We need to go and adjust the window. Right now the window is only going to 1551. We need it to go to at least 2500. So I'm going to come down here to my y max. I'm going to leave everything else. Well, I'm going to have to change my x max as well, huh? Because when t was 60, we were at 2030, and I know it's going to be more than 60, right? So my y max, I'm going to make y max 2600, and then for my x max, I don't know. I know it has to be bigger than 60. Maybe I'll make it 90. I can always come back and play if it's not there yet. There's the curve. It automatically adjusts. Ooh, I barely made it up there. Okay. So now second calc, 5 for intersect, enter. It's asking for the second curve, enter. It's asking for a guess, enter. The year will be, it'll be 72.695 years. Let me write that down. T is equal to 72.6954. That's how many years after 1970. So during what year is that? During what year is that? Well, 2030 was T is equal to 60. So it'll be in 2042. That will be the year that the population reaches 2.5 million. Okay, how do we like this so far? Very interesting, very different, huh? Different is okay. All right, let's do another example. And look at my time, yeah. Okay, a pumpkin tossing contest is held each year in Morton, Illinois, where people compete to see whose catapult will send pumpkins the farthest. One catapult launches pumpkins from 25 feet above the ground at a speed of 125 feet per second. The table shows the horizontal distances in feet that the pumpkins travel when launched at different angles from this catapult. A quartic regression is used this time to determine the model. And we're going to call that function d of a, because d is the distance, the output is the distance, the input is an angle in degrees. Okay? So, time to input the data. So I'm going to go to Stat, Edit, Delete, and Delete. It's rather satisfying to see all of those values just disappear. Okay, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, and 70 degrees. Enter at the last one, or it will lose it. Okay, distances in feet. 372, 462, 509, 501, 437, and 323. Okay, I'm always going to check to make sure that I got those in there correctly. And they look good to me this time. But I always check that. All right. Do we want to do see those? Let's see those. I turned off Y1 by going to the equal sign and pressing enter. But you know what? I'm going to be overriding that anyway. Notice that plot 1 is highlighted, so it will still show the data. Okay? If you wanted to turn that off, you just go up here, scroll up, and hit enter right there, and it will turn off that plot. But I do want to see it, so I'm going to hit enter on it, and it will show me my stats in L1 and L2 because that's how I set plot 1 to be. All right. Zoom 9, and it will give you a nice window to see your data. Okay, when I first look at this data, to me it looks like it might be quadratic, but they didn't tell me to use quadratic, they told me to use quartic, so I shall. So I'm going to do a quartic regression, so I'm going to go to Calc, and then quartic is number 7, L1 and L2, leave frequency list blank, and I'm going to store that in for Y1, so F4, Y1, calculate. There is the quartic equation. They gave me all of the coefficients of the x's in the quartic equation, the regression model that fits this data. Wow, look at that. That looks like it's going to be a nice fit. Let's graph it and see it. Holy smoke. That looks like an awesome fit for this data. right? Okay. Part A, use D of t to determine how far the pumpkin goes if the angle is 57.8 degrees. This time I think I'm going to use the calculate button. So I'm just going to do second calc value. It's asking me for the x. And remember, x is our angle. So I'm going to put the angle as 57.8. There it is. How far does it go? It goes 455.694. Give at least 3 values after the decimal point every time. And this is in feet. Okay. Now we're going to determine the angle that the catapult should be set at so that the pumpkin goes exactly 400 feet. Well, let's go to y equals. We want the distance to be 400 feet, so 400 goes in for another y. Graph that. There are two angles that will produce a distance of 400 feet. Two distances. Second calc 5, enter, enter. Now it's asking me for a guess. I think I'm going to go get this lower one first. Remember that these were our angles. I remember that this was 20 degrees. This was 30 degrees. I'm just going to do 20 for my guess. You can always input a guess like that. The intersection is this many degrees and this many feet. So 22.740, at least 3 digits after the decimal point every time unless they tell you to round. Okay? Now I'm going to go get this answer. So second calc again, 5 for intersect. Enter on the first curve, enter on the second curve. Now this time I think my guess, I'm going to use the 60 degrees. So my guess will be 60. And it is 63.6920 degrees. Okay? At least 3 values after the decimal point. Using the approximation model, using your model, what angles should the catapult be set at to produce the farthest distance? What is the farthest distance that the pumpkin will be chunked using this model? Well, whatever height that is way up there, that is the maximum distance according to this model. Let's go find it. Second calc maximum 4. It's asking me for a left bound, so I'm going to scroll, or I could hit a value. I could have just typed in a value. I'm going to scroll anywhere on the left of that peak. Anywhere on the left of that peak. You do not have to get it right up on there. I could have typed in 20 or 30 or 35. Okay, I'm going to hit enter. Now I'm going to scroll to the other side of that peak. It doesn't matter how far on the other side as long as it's on the other side of that maximum. Hit enter again. Now it's asking me for a guess. I don't care. I'm just going to hit enter again. So there's the maximum, and it's flashing. I know it's on the right spot. You know you're done when you see maximum there. So the angle that angle that produces it will be 43.6724 degrees. The distance will be 512.652 feet. So That's the power of these models, you guys. You can take some data, use a regression, and optimize what you need to do. How else would you know to set the catapult at exactly 43.6724 degrees, right? You wouldn't know. Okay, I have one more example here. Okay, baby blue whales, known as calves, normally weigh about 6,000 to 8,000 pounds at birth. They can grow about 200 pounds a day for the first year of their life. The weight of one blue whale is given in the table above, where the weight is in pounds and the age is in months. A natural log regression is used to model the weight function. Okay, let's go do it. So to stat, edit, delete everything. I'm going to put the age in for L1. So these are in months. Okay, and then over here and for L2, I'm going to put the weight in. Okay, those were some big numbers. I'm definitely going to look. I'm looking as I'm talking. I'm checking out all of these values to see if I messed up anything. It is super easy to type in something wrong. Okay, I think I did okay this time. Okay. Let's take a look at the data. So I'm going to go to y equals. I'm going to clear y1 and y2. Plot 1 is still highlighted. I'm going to do zoom 9. And there is those are the points, right? I can see that I have my x. I can see that on my y. On my y scale, thought it was on 0. My x scale is on 1. I'm going to turn off that x scale to make it cleaner. Okay, now you don't see all those little hash marks. Okay, because it was showing 132 hash marks down there, at least. Okay. Does it appear that it could be natural logarithmic? Does it appear to be logarithmic? We know about the equation of a log graph. Does it appear to be logarithmic? I think that's probably reasonable. Yeah. Let's go get the regression. So I'm going to go to Stat, Calc. The logarithmic regression is down here. Don't forget, some of your problems that you're going to be doing tonight have an exponential regression, and that is lower than that. And remember, there's also a power regression. There's also a logistic regression and a sinusoidal regression. We'll do that after we do trig, okay? But now we're going to go to number 9, logarithmic regression. It's the natural log regression. L1, L2, frequency list leave blank. I'm going to store this in for y1 and calculate. So there's the form of the log regression. A plus b ln of x. There's a, there's b, and there's our r squared. Looks fairly reasonable. Let's go graph that. Yeah, I would say that that is fairly reasonable. Yeah? Let's answer the questions now. according to the model, how much did this whale weigh in pounds at 9 months? Okay, at 9 months. So look at our 9 months would be between, it should be between these two numbers, right? So I'm just going to use that value function again. So I'm going to go to calc. Number 1 is value, and it's asking me, what do I want my x to be? I want my x to be 9 months. So it looks like the weight will be 112,445.38 pounds. Okay. I want to show you something on our home screen. If I hit Y, Y is right here. If I hit Y, so I'm going to go alpha Y, and it pulls up Y. It's going to tell me what value is currently stored into Y. It's going to give me that number, FYI. If you ever wanted to get that and store it somewhere, you can do it that way. All right. According to the model, how many pounds will the whale weigh at 12 years? 12 years. Well, 12 years, remember, our data is in months, so 12 years would be 144 months. So since I'm on my home screen, I'm just going to do Y1 at 144 months. 265,321.385, at least 3 numbers after the decimal point. Okay, I'm taking care of my daughter's bunny, and he wants a little pet, so I'll be right back. So this is my daughter's bunny. This is Charlie. Isn't he the sweetest thing? But I have my little workstation up here in the room that when I am taking care of him, he has to stay in this room. So anyway, every so often he will come and put his little sweet paws on my feet, and that means he wants a little attention. So this is the first time I've ever shown him on video before, so you should feel special watching this video. Okay, I'm going to go back to our problem, our whales. Okay, sweetness pie. Okay, sweetness pie. Baby. Oh my gosh. I thought that I had paused this again. I'm sorry about that. I would say that I'll go and edit this video, but I don't know how to edit the video, so you got what you got. Okie doke. Alrighty, where were we? According to the model, at what age did the whale weigh exactly 100,000 pounds? Exactly 100,000 pounds. So we're going to go to Y equals, put 100,000 in for another Y, and hit graph. There's 100,000. Second calc. 5 for intersect. Enter, enter. Guess, enter. You know you're done when you see the word intersection. So when Y is 100,000 pounds, the whale, according to this model, the whale is 7.1815 months old. Okay, so hopefully this was very doable for you. I think it's extremely interesting that we can use our calculators to get a very good model for a set of data. Okay? Alrighty. Now it's your turn. Go try the worksheet. Alright, that's it.